Okay, we are now in the process of discussing iterative methods. I recognize it's a little bit brief. It's a little bit brief on the transparencies, so I may make some amendments on the blackboard. The idea is to come step by step to more new and more efficient methods. But of course, we need some sort of a measure. And as a measure, we take our standard problem, that is the Laplacian, the 5-point stencil discretization of the Laplacian for the Laplacian with Dirichlet boundary condition equals to 0. And the dimension should be that our overall dimension m, which is the dimension of the set of equations we would like to solve, is n minus 1 squared. So that is not 100% consistent with the notation we had in the beginning. So that means we have n plus 1 points in each of the two spatial directions. So we have n minus 1 interior points. So this is the amount of interior discretization points which we have. So, and the point is with the Laplacian, with the discretization matrix which comes out, we can explicitly write down the eigenvalues. So we can compute everything what we need to assess the accuracy of a method. We can compute the condition number, everything what we need. So the eigenvalues, I gave them to you. The eigenvalues of AH first, of the discretization matrix, is 2 times 2 minus cosine k pi over n minus cosine L pi over n. So this is this n from here, and the L is running and the k is running between 1 and n minus 1. So we have n minus 1 squared, we have m single eigenvalues, corresponding eigenvectors, which I'm not going to write down. The eigenvectors are just discrete sine curves, which get more and more higher, more frequent. And as we are in 2 dimensions, it's just the product of the one-dimensional sine curves. And that's also the reason why we can so easily write down here the eigenvalues and the eigenfunction or eigenvectors. So if I would now write down the eigenvectors, of course, you could just check that these are the eigenvector to these eigenvalues, multiply the matrix with the vectors, and see vector times vector comes out. So, okay. That's the first thing. And if we now talk, we start with the Jacobi method as the most simple method. And the Jacobi method has an iteration matrix M. Let me also call it MH to indicate that it's really the question how the convergence behavior depends on the H. That we really want to see what happens in the situation if the H gets small, if the dimension of the set of equations becomes large. The MH in this case is just, what is it? We have minus the inverse of the diagonal matrix, but the diagonal matrix only has 4s. So we look at the version where we have multiplied already with the h square factor. So we have minus 1 over 4. That is just the multiplication with the diagonal matrix. And then we have here A times the diagonal. The diagonal is 4 times the identity. So what we have here is the identity minus 1 over 4 times AH. And of course, and this will always be the case, as the matrices which appear as iteration matrix will be matrix polynomials of the original matrix as we have it here, we can directly compute the eigenvalues. We know if we do a matrix polynomial instead of the matrix, then this matrix polynomial has the same eigenvectors, and the eigenvalues are the values which is the polynomial gives us applied to the eigenvalue. So what we have to have here, we have to look at 1 minus 1/4 over those values here. And okay, let's just write it down. So we have 1 minus 1/4, so this part goes away. And then we get, instead of a factor 2, we get a factor 1/2. The sign changes, and we have here the cosine plus the cosine. So what we like to see is the spectral radius of this matrix, because this is the contraction number as we figured out, or this is the minimal contraction number which we could get. And yeah, what does that mean? We have to compute the maximal eigenvalue, and where do we get it? We get maximal values if we make the k and the l as small as possible, then we are as close to the 1 as possible, or we go as close as possible to the n, then we are as close as possible to the -1 in the cosine. So we get out here either cosine of pi over n, and we can also write it, not sure we will need it, cosine minus cosine over n minus 1 pi over n. So to speak, the extreme values 1 and -1 are excluded because of the Dirichlet boundary conditions. Yeah, and that is pretty disappointing, because that means if we now take the series expansion of the cosine, we have here something like 1 minus pi squared over 2n squared plus higher order terms, that is, terms of the order at least of n to the -4. That means, okay, this is less than 1. We have a converging method. But the larger the n gets, the more we get closer to 1 here. So that means by increasing the dimension, not only the amount of work we have to do to do one iteration increases, that is natural and unavoidable. And in the case of our sparse matrices, so this should be O of m, but also the amount of iteration increases. Okay, so let's see what this really means. The amount of operations which we need for a relative error level epsilon is, and then you have to take, so what we do? We would like to have that this error is less or equal to an epsilon times the initial error. And what we can guarantee is that the error is less than the corresponding power of rho. So we have to assure that the kth power of rho, say, that the kth power of rho is correspondingly less than or equal to epsilon times the initial error. If you logarithmize the whole this whole relation and solve it for k, then you get the following relation for k. K should be bigger or equal than, you get here the logarithm of 1 minus 1 over epsilon. This, okay, we consider as a fixed factor. This is the level, this comes from the level we would like to see. We don't want to see now the influence of epsilon. Of course, this also plays a role. later has to be considered if we do nested iteration, things like that. Now we want to see the influence of the n, respectively the m here. Okay, then we have minus logarithm of rho to the m, and then times the amount we need for one iteration. This is capital O of m. So the ideal situation would be, in the end, we will formulate methods which are ideal in this sense. The ideal situation is that we have a uniform in H, or correspondingly in M, a uniform bound of the rho less or equal than some constant less than 1. That would mean that would be a constant, and we would see an optimal method which is linear in M. In terms of the complexity, this cannot be increased. We need M operations to write down the solution. So this complexity cannot be made better. But what is on the very other side of the spectrum is using Gaussian elimination without taking care of anything, and that is then big O of m to the 3. So we are somewhere in between. And the more close we are to the exponent 1, the better we are. So let's see where we are here. Here we are now. Okay, we have again this logarithm of 1 over epsilon. Don't care. So this term now gives, why is this? So we have to compute a logarithm of a quantity of this type. But logarithm of 1 plus x is up to higher order x. So we get here basically this factor, the whole thing inversed. The minus goes with this minus, and that means we get here a capital O of n squared times O of m. Or what do we have up to the log of the epsilon term? We have O of m squared. Okay, we are better than just applying brute force Gaussian elimination. But of course that we would never do to apply brute force Gaussian elimination. If we would do Gaussian elimination, we would certainly do it in a banded way. So let's compare banded, Gauss, or Cholesky. In this case, it's better to use Cholesky because we have a symmetric positive matrix. And in this case, we have, what do we have? We have bandwidth squared. We worked this out some time ago, bandwidth squared times m. So bandwidth is here n, O of n is the bandwidth, assuming that we take a row-wise ordering of the nodes. Of course, we could also take other orderings which make the band worse, but corresponding to the we are here in the square situation, so row-wise or column-wise doesn't make a difference, and then we should take the row-wise ordering. So this is then O of n squared times m. So this is O of m squared. Okay, we are as good as banded Cholesky. That's what it says. So now all the coming considerations will be to go down here. And only in the very, very end, if we speak about the multigrid method, we will see a 1 here. In all the other cases, we will see something bigger than 1. And it's clear what we have to do is, the aim is, we would like to have methods. I'd like to have a method such that rho of the corresponding iteration matrix is of the type 1 minus n to the minus alpha. Here we were in the situation alpha equals to 2. So we would like to have with alpha less than 2. Okay. And of course, alpha equals to 1, alpha equals to 0, then would be optimal to have just a constant here. This is, let's put it in parentheses. Okay, so let's see what we can do. The Gauss-Seidel method is not a solution for this problem. The Gauss-Seidel method, in its best situation, where we can really compare the rates of the Gauss-Seidel and the Jacobian method, and we have formulated, at least here, corresponding conditions on the matrix, and we will later see it again. So in principle, everything is possible concerning the relation between Gauss-Seidel and Jacobian. But if we look at matrices of the type which appear here, then it's typical that that we have the relation. What we have here is that the contraction factor of the Gauss-Seidel is the square of the contraction factor of the Jacobian. Look at the logarithm. This means that we get a factor 1/2 here. Okay, a factor 1/2 is a nice thing to have in the amount of operations. And of course, it's a different whether I do 10,000 or only 5,000 iterations, but it doesn't change the asymptotic behavior. Okay, so the first attempt, which we now try to do, is to do relaxation, what we have here on the transparency. That is, we have a method given by M and N, a consistent method, and we relax this method in this sense, and we asked ourselves, is there a good choice for this relaxation parameter omega such that now the convergence behavior of the method becomes better, or even if the original method did not converge, can we make it converging? And the most simple iteration you can think of is the Richardson iteration. Who has heard this word already? But nobody. It's too simple. It's the same Richardson from the Richardson extrapolation. You have heard of this? Okay, the Richardson iteration. And the Richardson iteration is extremely simple, and the consequence is that there are hardly any situations where the Richardson iteration converges. If you would like to see a situation where it converges, then you have to come at 4 o'clock. So what is the Richardson iteration? So we have a matrix A, and as matrix M, we just take the identity matrix, as matrix N, so the matrix which is responsible for the simple set of equations to be solved in each iteration step is taken as the identity matrix, and of course correspondingly also the inverse is the identity matrix. And therefore by consistency M has to be identity minus A. So what we are doing is we are just extracting, so to speak, an x out of the equation, and do I have a proper piece of... Okay, it's not written down, then I have to do it on my own. So how was it? So I have here xk, and then minus n times, but n is the identity, minus axk minus b. So that is the Richardson iteration. I've just added this part here to the corresponding residuum equals 0 equation, or minus residuum equals 0, and I iterate over the x. I have no auxiliary set of equations to solve in each, not even with a not even with a diagonal matrix or whatsoever. So it's most simple what I can think of. Okay, the consequence of this that it also hardly converges, namely, what is now the situation here? When would this converge? So, wo ist die Seite jetzt? Okay, here. Now let's write down the spectral radius of M. This is the maximum either taken of 1 minus lambda max of A and modulus and 1 minus lambda min of A. In general, there's no reason for this number to be less than 1. If we have at least a symmetric positive definite matrix, meaning that we have positive eigenvalues, then all our eigenvalues, then we can assure that the values we are looking at here are smaller than 1, but we cannot assure that they are bigger than minus 1. So also, even in this case, we have no convergence. What we are now going to do is we look at the relaxation procedure and find a parameter omega such that the method converges, and see what we can take from that. Why it is worthwhile to look at such a ridiculous iteration? In some sense, if we combine what we are doing with the idea of preconditioning, which we will do later on much more extensively, the Richardson iteration is the iteration. What do I mean by that? So my conjecture is a general iteration. Iteration always means linear, stationary, consistent. A general iteration corresponds to preconditioning conditioning plus Richardson. So a general iteration looks like that. xk plus 1 equals xk minus n times ax minus xk minus b. So let's assume what is always the case in all the examples we will look at, that n is invertible. In fact, I said, actually, it's not the matrix N what we have, it's its inverse, it's the matrix W. The matrix W is a sparsely populated matrix, the matrix N. It's not advisable to compute it because it would be fully populated. So applying the matrix N always means applying W to the minus 1, that is, solving a set of equations with the system matrix W. So if n is so we could do the following. So the preconditioning, what means preconditioning? We will do this later more precisely. Preconditioning could mean I have my set of equations, ax equals b, and I multiply that set of equations with an invertible matrix. From left, I could also do it from right, in the sense that I transform my variable. Of course, with the idea that this set of equations is now easier to solve, that I get closer to identity here. So, if I would do the preconditioning, and if I now do Richardson for this situation now, what does that mean? Richardson is n tilde, let's say, equals to identity. So Richardson means, just write it down again, xk minus 1 equals xk minus n tilde. And now I have the residuum of this equation, which is just n axk minus nb. So it's exactly the same thing as here. So doing a general linear stationary consistent iteration method just means doing proper preconditioning plus Richardson. So it's worthwhile to look at Richardson and to get it by relaxation more efficient. So we do now the relaxation for Richardson. And what does that mean? Here you have the formulas. You have the corresponding formulas for the m omega and the n omega. And now we have to compute the eigenvalues of this new. So we do relaxation. I do not write this down here. And we compute the eigenvalues. So what do I have to do with the eigenvalues? I have to multiply with omega, and then I have to add 1 minus omega times 1. So the eigenvalues are omega lambda I of m plus 1 minus m, or 1 minus omega 1 minus lambda I of m. So, and now we ask ourselves again, what is the spectral radius of this? And we get basically the same formula as above here. That is, we have maximum 1 minus omega 1 minus lambda min of m, and the corresponding thing with 1 minus omega 1 minus lambda max. So the first question is there an omega such that this expression is less than 1? And then the next, if we could do so, of course, we could be a little bit more demanding and say we would like to find the best omega. So we would like to find the omega which makes this expression minimal. Can we compute this omega? I don't want, the computations are quite elementary. I don't want to go through all the details. You see what we have here? We have here a straight line. Now in the eigenvalue we have a straight line. If we fix the omega and we see the relation in lambda, this is a straight line. And for lambda equals to 1, we have the 1. So we're looking here at straight lines for fixed omega to compute this quantity. We're looking here at straight lines all going to 1. So the picture is, so if I call f lambda for a fixed omega, say 1 minus omega 1 minus lambda, that's what I have here. I have to look at straight lines which are here at 1. They all go through 1. And now it depends how otherwise they lie. So, okay. So of course they can get negative, and then I have to flip them around. And now if I plot the whole thing in dependence of omega, the picture is as follows. Now I have here omega, and I have the maximal and the minimal lambda min and lambda max, and then the graph either looks like that, So, and if I now look at the same thing for lambda min is a smaller value. So I lie below. I have to go through 1, I said, so I lie below. That is looking at the modulus. I have to flip it around here. And correspondingly, of course, also this then later on. Okay. So, and you see, now from these two values which I have to take the maximum. And the question is, when do I get the smallest of all the results? And I hope this is a little bit convincing, this picture. If I'm away from this crossing point here, then I have a small value from this here, but a large one from this, or the other way around. And the best situation I get here. So my omega opt sits here. So my omega opt, or omega bar, I have denoted it, omega bar is such that, that's the definition, that now the spectral radius is the minimum of all the possible spectral radii which I get. It doesn't mean that I have convergence there. It could still be bigger than 1. Let's see what comes out. So this relation tells me I have to compute 1 minus omega bar, 1 minus lambda max. I abbreviate it a little bit and let the m go away, equals, and now the negative of the other, minus 1 plus omega bar 1 minus lambda min. Okay, this I can of course resolve for omega bar, and I get the following formula: 2 over 2 minus lambda max minus lambda min. And then you see already the problem which comes in. In principle, I can compute this number. But of course, I do not need to know the whole spectrum, but I need at least to know the maximal and the minimal eigenvalue. Then I can compute this. But of course, to compute an eigenvalue is in general a much stronger task than to solve a set of equations. So there lies a problem. Let's ignore this problem for a moment and let's see what we have achieved. And what we have achieved now is, if we now compute what the spectral radius at this point is, then we have to take one of these two lines, either this one or this one, and evaluate it at the omega bar. So we have 1 minus omega bar, 1 minus lambda max. And if you look, plug this in and so on, then you see here this is less than 1. So by optimal relaxation, we can make the Richardson iteration converge. Okay, now let's see what do we have for the model problem. This was on the blackboard which I erased. On the so. Okay, maybe I have to make a further comment. That what we did up till now, that was now a general statement about relaxation. If we now do it specially, in particular for Richardson, that was for any basic iteration and the corresponding relaxation. If we do it in particular for Richardson, then the formulas get a little bit simpler. Then M is identity minus A. And then here those, maybe I should not have made it. Okay, I remind again. So here we have to have the eigenvalues of the, not of the matrix A, but of the iteration matrix M. But now in Richardson, M is identity minus A, so this corresponds to the formula for the eigenvalues. So the maximal is 1 minus the minimal, and so on. So in this case, then, this omega bar formula then simplifies to 2 over lambda max of A plus lambda min of A. But of course, this remark that I said, in principle, the computation of the eigenvalues is more expensive than to solve the set of equations, still holds true here. Okay. So what does this mean now for the spectral radius? This is this formula. So 1 minus lambda max is now lambda min. And this becomes, if we plug this in, lambda max A minus lambda min A over the sum of these two quantities and this we can now relate to the condition number if we take the spectral condition number. The spectral condition number in the case of, let's talk about the situation of a symmetric positive matrix. In a spectral condition number is maximal eigenvalue divided by minimal eigenvalue. So if I divide everything here by lambda min, I get here condition number minus 1 over condition number plus 1. Okay. And if we would like to see the others we had in this form, 1 minus a term which then was of the type O of n to the minus alpha, let's see that we get the same thing here. So I write this in the form 1 minus. So what is this? This is then 1 minus 2 over k2 plus 1. And the condition number is a big number, as we will see in a second again. This, of course, I can then approximate by 1, 2 over the condition number. Okay. Now what about the... Okay, now that is the situation for Richardson. That was general, that is for Richardson, and now let's apply it to the model problem. So we have to compute the optimal omega from the formula. For the model problem, we know everything, so we can really do that, which is unrealistic in other cases. So we first need the omega bar. So we have to add lambda max plus lambda min. Where is it? Wo ist meine Seite 102? Ah, here it is. Okay, what was this? The maximal eigenvalue we got, I write down the formula, then you will see what comes out. So that is the formula which comes out. Why? The maximal eigenvalue we get if we subtract the minus 1s. The minimal eigenvalue we get in terms of the cosine. the minimal eigenvalue we get if we subtract the ones, or something close to -1, something close to 1. If we add this all up, this ends up in this term. And now you see, here we have the symmetry relationship of the cosine. If we, instead of x, I consider pi minus x, then the cosine changes its sign. So these two values cancel. That is, what comes out is here just 8. So omega is 1 over 8. Sorry, I forgot the 2 here. Is 1 over 4. That should ring a bell. That means instead of using the diagonal with the 1s, we use the diagonal with the 4s, or inverse with the 1 over 4s. That means in the end of the day, so what is now M omega, the iteration matrix, is now identity, not minus A, but minus omega bar A, so 1 over 4A. And that is M Jacobi. That is, by optimal relaxation of the Richardson method, we have reinvented the Jacobian method, which is not really a breakthrough. Okay. So, and of course, what is clear, that of course now the convergence behavior is the same, that the condition numbers are the same. We can compute the condition number. This is now an equality. And if we do this here, we see that we get this dependence in n square. So we get a dependence in 1 over h square. And we remember that we had this estimate of the condition number of the stiffness matrix, which exactly said this is an estimate constant times 1 over h square. But as it was only an estimate, it was not clear at the moment, is it a sharp estimate? Maybe it's much too pessimistic. And this example tells us it's a sharp estimate. And the behavior, and turn it the other way around, we can say, due to this same behavior of the condition numbers, the same convergence behavior which we see here for the model problem we can expect for a more general problem, at least with a quasi-uniform triangulation. Okay, so now we would like to do something different. So we have to do the relaxation a little bit differently. And doing the relaxation a bit differently leads then to the so-called SOR method, successive over-relaxation. Ein bisschen viel jetzt. Das lassen wir. Who has heard this name already? SOR? Okay. So we can be a little bit more brief with that. The SOR method, there's of course also a history in these methods. And talking about Jacobi and Gauss-Seidel, of course, we are speaking about the times of Gauss, where a processor was a human being at that time, not something in a machine, of course. Talking about the SOR method, we are talking about computations in the, say, 50s to 70s. And later on, we will come a little bit to at least to the present. So what is the idea with the SOR method? The SOR method is a relaxation of the Gauss-Seidel method, but done in a different way. For the SOR method, the Gauss-Seidel method is written in this form here, in a non-resolved form. So you see here the diagonal matrix, the lower triangular matrix, the upper triangular matrix, and here, as it is Gauss-Seidel, already the new iterate is used. But we keep it in this form. We do not bring this part to the other side and multiply with d plus L inverse. So we do not solve this incorporated triangular system, but we keep it in on this level, and we do the relaxation here on this level. That means we take this part only with a factor omega, and with a factor 1 minus omega, we use the old iteration. Okay, one could do that, and if one does so and now resolves, there's no formulas whatsoever on these transparencies, so I have to write it down. If you now work out the iteration matrix, so we call this relaxation SOR. This stands for successive over-relaxation. At the moment, it's not clear if what kind of omega is good. Later on, it will turn out that one should take an omega bigger, and usually should take an omega bigger than 1. One should over-relax, one should go, in this sense, beyond the iterate. And therefore, this name over-relaxation. So in general, one speaks of over-relaxation if the omega is bigger than 1, and under-relaxation if the omega is less than 1. So the problem with the analysis of the SOR method is, if you look at these formulas, I'll just write down one. Of course, it's easy to figure this out. This, for example, is the iteration matrix. For omega equals to 1, this is supposed to be the iteration matrix of the Gauss-Seidel method, which really it is. But what is the problem now? This iteration method, a matrix opposite to the iteration method we had here, the iteration matrix depended linearly on omega, and therefore it was easy to study the dependence of the eigenvalues and of the spectral radius on omega. Here we now have a nonlinear dependence, which makes it much more complicated to study that. Okay, let's bring in also this matrix, which is the matrix which relates to the problem which we have to solve. So times omega. So this is the triangular system which we have to solve as an auxiliary step in each iteration. So now we can ask ourselves the same question. Is there good or is there an optimal omega here? And I can only refer a little bit to the theory. Maybe you did this also already quite more general. Before doing so, let me indicate some variants of this method. A further variant of this method is the so-called SSOR. You heard this also? So, the symmetric successive over-relaxation method. Yes or no? No? What is the problem? In the case when we are dealing with a symmetric matrix, let's say positive definite symmetric matrix, the set of equations which we have to solve here, you see it here, is of course, let me put it another way, you see it here, the iteration matrix is not symmetric. In the SSOR, you do the following. So what you do in the SOR, you solve a set of equations where you have this matrix times 1 over omega as the system matrix for this system to be solved. Of course, this means that the numbering of the iterates, the numbering of the component plays a role, as it already played a role with the Gauss-Seidel method. Now, after such a step, one can say, okay, I've done this step, but this is not my new k plus first iterate, but I take this, maybe I call it k plus 1/2, and I do a further half step by starting with this k plus 1/2, doing again an SOR step, but now I reverse the order in the in the components. So SSOR, so one step in SSOR is one step SOR in the order 1 to m, plus one step SOR in the order m to 1. If you write this down, what does that mean? That means that the D and the L changes its role. At the moment it is so that the L matrix, because we start with 1, the L matrix is the one which should see already the new iterates. But if we go from the back, then it's the R matrix which should see already the new iterates. So the only thing what happens that L and R changes their roles here in the formulas. And if you write all these things down, which I'm not going to do, we really see that the outcoming matrix has better matrix structure. Of course, the effort to do one iteration is enhanced, but it's not really factor 2. It's less than a factor 2, because in setting up the vectors and matrices which you need to do the second step, there are things which you have computed partially already here. So it's a little bit less than a factor 2. Of course, this, if it would make sense, it has to pay off then also in the... So that is the one thing. And then the other thing is, independent of SOR and SSOR, but of course also applicable there, are the so-called block iterative methods. In the block iterative method, the idea is we partitioning our matrix in blocks. So we have here a block A11 and so on, diagonal blocks. How many do I want to have? P can also have something to do with processors. So these are also methods which are go in the direction of parallelization, and correspondingly here A1P and AP1. And then we partitioning, of course, our X in X1 to XP. So these are now not components, these are vectors, smaller vectors. And correspondingly here the right-hand side. And now we apply any method we would like to do. We could start with Jacobi, that would be then a block Jacobi or a block Gauss-Seidel or block SOR, and apply it in this block structure. That is always in the case where we have to divide by the diagonal element in the Jacobi method or in the realization of the Gauss-Seidel method. We now have to solve a small set of equations with this diagonal matrix as the corresponding system matrix. That means this is advisable in particular then when those diagonal matrices have very simple structures. For example, if these diagonal matrices are symmetric matrices, even if the other matrices are not symmetric matrices. Or put it another way, the structure of the off-diagonal matrix, let's only think of Jacobi now for a second. If we only think of Jacobi, then with the off-diagonal matrix, we only do matrix times vector in the iteration. So a special sparsity pattern we do not need. Of course, we don't want to have too many entries, but where the entries are doesn't play a role by the operation vector, matrix times vector. Only by the operation solve a set of equations, then the hull, whatever, the band, and so on plays a role. So one nice situation could be if we could have here diagonal matrices and maybe a bad sparsity pattern in the other matrix. But this, for example, we can get if we do the following. Now let's say Jacobi. What does that mean? Maybe I write down Jacobi, and Jacobi is now xi k plus 1 equals aii to the minus 1, and here I have bi minus sum over the aij's xjk, j from 1 to whatever p, j non-equal to I. And if I want to have not Jacobi, I want to have Gauss-Seidel, then I have to modify this here correspondingly. But the idea has not changed. If I want to have a relaxed method, then some omegas are popping up here. So I could do the same thing also with SOR, for example. I could also do block SOR. So what would be an example? So I said it would be very advantageous. It would be advantageous. Let's go again to full light. It would be advantageous. So it's desirable, let's say, desirable that aii is diagonal. Then this, how can we get this? We can get this, for example, with p equals to 2, but also with higher p can do the same idea by doing multicolor numbering, how this is called. In the most simple case, a red-black numbering or a checkerboard numbering. What does that mean? Let's say this is our domain omega. So those things which you see here are the grid points. Okay, we have the nodes, let's say 1. How many do I want to have? I want to have 5 in one direction. And then I have here 6, 7, 8, 9. Oops, do I have a 10 also? Why don't I have a 10 here? Okay, let's stick to 9 nodes. Then we do it the other way around. We do it in a square. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, and now we subdivide those nodes. So this is our omega. Now we subdivide these nodes in 2 sets. In the first set, we collect the nodes 1, 3, 5, 7, 9. And in the second set, 2, 4, 6, 8. So now if I do, that would mean I do the numbering 1, 2, 3, 4, 5, 6, 7, 8, 9. So I had a mistake somewhere. So what does that mean? That means according to our 5-point stencil, let's say I have a point in N1, let's say 5, that he has the full set of neighbors. All its neighbors are in N2. Or for example, 6 from N2, all its neighbors are in N1. If I now take this, so to speak, this new ordering, which I indicated here, that means that if I write down the components in the corresponding row, I get a diagonal matrix as the block diagonal matrix, and all the other parts go in the off-diagonal block. I enlarge the band enormously by this procedure. So for a banded method, that would be total nonsense. But for this block iteration, it would be a good idea, because the thing which I have to solve, namely here, this subsystem, this now becomes simple. And then similar things one can do. One can, for example, say, okay, it's okay if this is a tridiagonal matrix. That would mean that I collect in the one set all the x neighbors, and I put the y neighbors in the other set, for example, and I can play around with this. Okay, so what can be done with the relaxation, this nonlinear relaxation here of the Gauss-Seidel method, that could be also in principle done with block variance, block variance of the method. Now let's see what comes out for the SOR method. And this, at least I think we have on the transparency, hopefully at last. Okay, yeah, partially we have it on the transparency. I said it's very difficult to analyze, it's tedious to analyze the SSOR, or the SOR method, and also, of course, then the SSOR to this nonlinear dependence on the omega. And one needs certain condition on the matrices. And these conditions are pretty much counterintuitive. I can give you the definition, and then you will say, okay, that's a definition, but it's not clear which matrices fulfill this definition or not. But nevertheless, I think I have to do that, in particular as we have an exercise to prove this requirement for our specific matrices. And this is the condition of being consistently ordered. So a matrix A, real matrix MM, as usual, is called consistently ordered. If we have this again, this additive decomposition in D plus L plus R, and on with these ingredients as we do, for example, SOR. So we would like to have D is non-singular. Okay, that is not a big requirement. And now it comes. I consider the following matrix depending on a parameter alpha. It's alpha to the minus 1, d to the minus 1L, plus alpha d to the minus 1R. And the requirement that this family of matrices for alpha bigger than 1, no, it's even harder for alpha being a complex number, alpha non-zero, has eigenvalues independent of alpha. That is the requirement. So it's really not clear to say which kind of matrices have this. The task of the exercise will be at least to assure this requirement for, so to speak, the model problem situation. And the theorem of what we can say under this condition is the following. The first thing is, and for that we do not need this requirement, is what we have here on the transparency. We have here a lower bound for the condition number, for the spectral radius, in terms of Jetzt war ein bisschen zu viel. And in terms of 1 minus omega modulus. That means, what does that mean? That means, okay, you should not go beyond 2. Going beyond 2 guarantees to you that the method is not converging. That means you should restrict yourself in the choice of omega to the interval 0, 2. This gives some space for over-relaxation. And, okay, in principle it will work in the sense that if the matrix is symmetric and positive definite, then the convergence is assured for all parameters. To have more, to see more, then we really need this, what I introduced, this requirement of consistently ordering, in the sense that then we can give a formula. The theorem, I don't write it down fully, but the theorem basically says if the spectral radius of the Jacobian method is known, and it's less than 1, that is, if the Jacobian method is converging, plus this condition here, then, let me put it like that, there's a formula for the spectral radius of the SOR method, depending on omega. And there's a formula for from this formula we can see omega opt. And namely omega opt is then 2 over 1 plus 1 minus beta square. This is this beta from here. And the square root. And if we have this, then we can also compute the spectral radius for this optimal relaxation parameter, which then turns out. This is then obvious from the formula, which I now haven't written down, is then beta square over 1 plus 1 minus beta square root and the square of the whole thing. And the shape of this function here, depending on omega, as we said, we should only look at the interval 0 and 0, 2, is the following. Somewhere there's omega opt, and we will see, one can see, the larger the matrices become, the omega opt is then moving to 2, so 1.8 and usually is not a bad number. And the function goes down in a sort of a parabola fashion, and then there is a straight line part. That is the shape. That means if you are not sure about the omega opt, it's better to overestimate it, because here you do not change your row too much to the worse as you would do it here. So what one can conclude is, in general, it's a good idea to overestimate the omega opt. And in very rare situations, it really can be computed. Now, if one, in the model problem, we have everything on our hand. We have computed already here the iteration matrix for the Jacobian and the spectral radius. I don't want to repeat now all these computations and just state what comes out for the model problem. For the model problem, if we do all these computations and we see what comes out if we take the omega opt, of course, then we have to check that the model problem really fulfills this property, but I think this is an exercise. And that comes out. We have, of course, our logarithmic in 1 over epsilon term, as usual. And now, where is it stated? It's not stated here. Wo ist jetzt die Seite? Ach, da jetzt hier. Okay. Okay, maybe I can do it a little bit more precisely. So what is this? This would be, in this case, 2 over 1 plus sine pi over n. This is what I said. It's a number close to 2. So with 1.8, you're always quite good. So what comes now out for the spectral radius? For the spectral radius, so we have now here 1 minus, and now it really becomes better. You remember we had here something like pi over n squared, and now we only have here pi over n. And the consequence of this is the amount of operations to reach the level epsilon is logarithm of 1 over epsilon. And now there comes the interesting part, O of m to the 3/2. So we are now down from 2 to 3/2. Of course, what is the problem here? The problem is we have a magic parameter in the method, the omega. And usually, a part of all these very specific situations where we can compute everything, we cannot get our hands on this omega. Of course, one could make a method out of that and could say, okay, I guess my omega. I do a few iterations, see how it works, then I modify it again and see whether it gets better or worse, and I modify it again. But this is another type of method. That's not a linear stationary iteration method, because I change my iteration procedure in the iteration. And what we now would like to see is, we would like to see methods which are as good as the SOR method without having these control parameters to be adjusted. And that the SOR method is already quite okay. You see here, again for our model problem, comparing the situation of the Gauss-Seidel method and the SOR method. Here the iterations of the Gauss-Seidel methods go up quite dramatically, and the SOR iterations are at a totally different range here. And even if one takes into account that there's something like a factor 2 or less than 2 in between in effort between one iteration here and one iteration here, of course this method is way superior here. But of course one had to know the optimal relaxation parameter. And as I said, we will now try to see methods which get also in this range, also have this kind of behavior without having control parameters. Okay, and this is now something which you should all know, but as it is Christmas, we can, it's always the wrong one which I make, switch off. As it is Christmas, we can do something which you have heard already several times, namely descent methods, and in particular then the conjugate gradient method. So let's start with this in the last minutes which we have. In this first attempt dealing with the classical conjugate gradient method, we have to restrict ourselves to symmetric and positive definite matrices. That's quite a restriction. It's an enormous restriction, because that means we can only deal with diffusive problems. All the convective part is excluded. And if we want to do this then in more general for non-symmetric matrix, a big deal of the efficiency of the conjugate gradient method is then also lost again, which does not prevent one from applying these kind of methods, which are then called in this more general version Krylov subspace methods. Who has heard this word already, Krylov subspace method? Of course, the CE students, they hear it 24 hours a day, but the mathematics students have never heard of Krylov subspace methods. Okay, it's never too late, so we do it here. Okay, first, but you heard of the gradient method, and I guess you have also heard of the conjugate gradient method. So what is this? The basic thing is that in the case of a symmetric positive definite matrix, we can, and we have seen this already, this was just the equivalence of the Ritz and the Gajerkin approach. The task to solve the set of equations Ax equals to B is equivalent in minimizing a quadratic functional with this quadratic part 1/2 x transpose Ax and with the linear part minus B transpose X. So this is a quadratic functional. This is, so to speak, a multidimensional parabola opened to the top. It's good, therefore it has a unique minimum. And as it is a parabola and not just any functions, the requirement that the gradient vanishes, that we have a stationary point, is not only necessary, it's also sufficient for a minimum, for the unique global minimum. And if we compute the gradient of this quadratic functional, then we end up with Ax minus B, that is the residuum of the original set of equations we would like to solve. So, and that is the reason you remember that I said as a stopping criterion, in general, one should use the residuum, so this quantity, to see how good this is already 0 or not, if I have some approximation x here. And we call this residuum G like gradient. That is the reason, because here it's the gradient. We are used to argue in the Euclidean scalar product, but here it turns out there's another scalar product which we know also already, which is here much more appropriate, namely the energy scalar product, the scalar product induced by the matrix A. So this is just our underlying scalar product of the weak formulation of the boundary value problem, then applied to the finite dimensional space. It's exactly the same thing which then comes out if you do not apply the scalar product small a then to arbitrary functions, but to functions from a finite dimensional space. And then this A is then the stiffness matrix for the corresponding basis, and the x and the y are the coordinates in the spaces. So, okay, what would be a possible method to solve this minimization problem? So the idea is we solve this minimization problem. We solve the set of equations via solving the minimization problem. So what would be a way to solve this minimization problem? We could do a search algorithm. That is, we do an iterative method. So we have some starting point x0, and the case iteration is done like that. We think of a search direction, and then we restrict this, in general, m-dimensional problem, which we have here to minimize, to a one-dimensional problem, in the sense that we only look in the direction of the search direction. And then we do this auxiliary, you see, it's always, again, the same ideas. Again, we have here a simplified auxiliary problem to be solved, and here it turns out to be a one-dimensional minimization problem. So what is written down here can be applied to any functional f. Then also this one-dimensional minimization problem would not be possible to solve this explicitly. But in our case, in the quadratic case, we can solve this one-dimensional problem explicitly. So we get this alpha, this step in the direction of the search direction, which we have to use here. And okay, and this we then use to set up the new iterate. And the gradient method is just to say, okay, I'm at some point xk, I want to descend, I want to decrease my functional value, and the direction which gives me locally the best, the maximal decrease is the negative gradient. So I take this here. So this is a method which is very appropriate now to winter time. Also, we would need a little bit of snow for that. So you take your sledge, you're on the hill, you take your sledge. You direct it in the direction of the steepest descent, and then you let it go. What would happen? Your sledge will end up in the minimum of this one-dimensional, on this affine space on which you are one-dimensional affine space on which you are traveling. Okay, then you are standing there. Then you redirect your sledge again in the direction of the steepest descent, and the thing goes on. Okay, this is the gradient method. This is very simple, but as usual, there are exceptions, but as usual with simple method, it doesn't work well. Okay, why it does not work well? We can have a look already why it does not work well. At the end of the day, and we'll see whether we will prove it or not next time, is this order of convergence which comes out. So we now have an estimate which is very similar to the linear stationary method in the sense that we have here a factor, and the corresponding power of this factor less than 1 appears here in the question how much the error is diminished from the initial iterate. The difference is here that we now measure the error in the energy norm A, but this number is very familiar to us. Condition number -1 over condition number +1. That's exactly what we have seen in the optimal relaxation of the Richardson method. And we have seen this optimal relaxation of the Richardson method is just, in our special case of the model problem, the Jacobi method. If you put everything together, that says we have no improvement whatsoever. It's just it's a new method, it's a different method. It's not identical with the Jacobian, but it behaves asymptotically as the Jacobi method. And we are not satisfied with this behavior, as we have seen. Well, we have to do something to improve here. And the conjugate gradient method will bring here a corresponding improvement. And maybe the last remark, why it is not so good driving your sledge in this way. You see it here. Your landscape is shaped by your matrix A. And therefore it makes sense to look at the geometry defined by A, that is at the energy scalar product, and not at the Euclidean scalar product. That I have here this ellipsoid-shaped landscape. This reflects that I have a small eigenvalue and a larger eigenvalue of A. Okay, in 2 dimensions I cannot have much more. And you see here what happens. I go down, come here parallel to this level set. So these lines here, all the level sets here of the functional. Then I turn my sledge around, and so on and so on. And you see here, from here to here, everything is nice. These directions are orthogonal in the Euclidean sense. They have to be, because I'm here in a minimum. And a minimum means my gradient has to point fully out of the one-dimensional space, has to be orthogonal to this one-dimensional space. Otherwise, I would have a component which allows me to decrease or increase. But if you look at this direction and this direction, so the first and the third, they are already quite parallel. And that means instead of really, so to speak, working through the full d-dimensional, okay, here it's only m-dimensional space, even if m is only 2 here, it takes quite a while, because I'm always come in these parallel situations again, in the zigzagging situation. And that is something which should be prevented, and the way to prevent is to have search directions which then really are orthogonal with respect to the Euclidean, with the energy scalar product, and this is what we call then conjugate directions. Okay, this we will do then on Friday.